In several of the recent episodes, we've seen Sabine Hossenfelder lamenting the pathetic state of science and pointing out huge problems in physics in particular. Recently, Professor V.J. Balasubramanian of the University of Pennsylvania pointed to what he sees as the real source of the problem.
Our best descriptions of nature, quantum mechanics and general relativity, are failing us. To dig into the deepest layers of reality, we're going to need new physics. In this video, we'll build a stage of space-time from the ground up. And then we'll see that we have no choice but to tear it all down again. And in the wreckage, we'll look for clues to paths forward towards a quantum theory of gravity. During our journey, we'll be forced to challenge our basic assumptions. Is space-time real or just a large-scale illusion? At the fundamental level of nature, do questions like where and when even have answers?
It shouldn't really come as a surprise that space-time has led us down a path of problems. In episode 44, we met Frederick Soddy, a pioneer of radioactivity and a Nobel Prize winner. We looked at a document which you can find on the Reformation Christian Ministries website. There's a section on science and scripture with one page from Professor John Bale, someone I greatly respect, and one page from myself. On my page, under the section What is Science, if you scroll down the General Considerations section, you'll find Soddy's address to Nobel Prize winners. The wider aspects of the discovery of atomic disintegration, contrasting the experimental facts with the mathematical theories. In my comment above the title of the paper, you'll see that I recommend every scientist and every science writer to read this paper. Soddy was very concerned that physics was becoming dominated by mathematicians with little understanding of real science. He pointed out that relativity became tied to a dimension, including the imaginary number I, a dimension of imaginary time multiplied by the speed of light. This was the first time that the imaginary number had not been either mathematically manipulated out of a result or interpreted as something to do with some real entity, like phase shift as we saw in episode 67. This naked imaginary number became an integral part of relativity. But that wasn't the end of it. As Louis Essen pointed out in episode 72, Einstein's relativity is not truly a physical theory, but rather simply a number of sometimes contradictory assumptions. Most physicists don't seem to even notice most of them. One of his assumptions was that there was no medium through which light propagated. Physics had, for a long time, depended on a medium they called the ether. Some of its properties had been measured. Maxwell's equations accurately predicted the speed of light based on one electric and one magnetic property of this ether. But one experimenter after another showed that the Earth was not moving through space, as we saw in episode 42. Scientists started frantically looking for a way to avoid the conclusion that the Earth was stationary at the centre of the universe. In episode 43, we saw Einstein coming up with a Letout based on banishing the ether. Scientists were gratefully prepared to accept Einstein's idea in spite of contradictions by experiments, two of which were performed by the renowned A. Michelson. Another of Einstein's arbitrary assumptions, which links with the first assumption, is that the speed of light is always constant to all observers, no matter how they, or the sources of light, are moving. He claimed it is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. That supposition has drastic consequences. The speed of anything is defined as the distance it covers in a period of time. If a car travels 30 miles in half an hour, its average speed is 60 miles per hour. This assumes that a mile is a constant and unchanging distance, and an hour is a constant and unchanging period of time. Speed is a dependent variable. It depends on distance measurement and flow of time measurement. But Einstein stipulated a speed to be a constant, which means that distance and time now must become dependent variables. Einstein later repeatedly admitted that the speed of light cannot be constant. For one thing, he claimed that light bends near large masses, and in doing so its speed changes. But the establishment was so horrified at the possibility of returning to the Earth being stationary at the centre of the universe that they ignored him. The speed of light is not a constant for all observers, no matter how they or the light source are moving. So relativity ended up with mathematical manifolds which have distances which vary to keep the speed of light constant. These imaginary manifolds bend in the presence of mass.
To get a sense for the mathematical model of space-time, let's begin with one flat grid. Now let's take another one, and another, and another. When we stitch them together, we create a mathematical object called a manifold. Let's imagine we're a cat walking on the surface of this manifold. Locally, the grid looks flat with straight-line coordinate axes everywhere. But if we zoom out, the manifold turns out to be made up of curved coordinate axes. Einstein's big revelation in his general theory of relativity is that space-time is a manifold that bends and curves in the presence of matter or energy. The effects of this curvature produce what we experience as gravity.
But there's another problem in physics. Before Einstein banished the ether, its existence had been a feature of the study of black body radiation by Einstein, Planck, Nernst, and others, as we saw in episode 79. There are physicists who've returned to their methods, working on stochastic electrodynamics theory. It can give answers to some quantum mechanics problems quicker and easier than quantum mechanics, using well-known, understandable classical electrodynamics. But after Einstein had abolished the ether, Heisenberg had nothing with which to interpret his uncertainty relationship. His quantum mechanics had to be built on a base of Einstein's new space-time, with its imaginary time multiplied by the speed of light. And surprise, surprise, it also supported a naked imaginary number in the form of an imaginary wave function.
To investigate space-time at the fundamental level, to really ask questions about what it's made of, we have to take a quantum point of view. This is the quantum stage. In this probabilistic universe, subatomic particles don't have fixed positions in space. Instead, they have amplitudes. Amplitudes are like probabilities. But unlike probabilities, they can be complex numbers, which means that amplitudes can cancel each other out. Quantum mechanics says that to go from here to there, a particle can take many different paths, each with an amplitude. These amplitudes must be summed up to find the total amplitude of that transition. So, on our quantum stage, physics is not described by saying where things are and how they move, but rather how amplitudes for different possibilities change over time. This evolution is described by the famous Schrödinger equation.
As we saw in episode 81, Tim Maudlin of New York University pointed out that quantum theory is not actually a theory. It's a mathematical recipe, or as Brian G. Wallace might have put it, a mathematical description of the data table. You put in numbers and get out very accurate answers, with no real understanding of why those answers should be valid at all. And if you ask why, the standard response is, shut up and calculate.
Ever since physicists realized that quantum mechanics is the underlying language of the universe, we've been trying to fit everything we know about nature into its strange laws. The result of these efforts is quantum field theory, a more sophisticated version of quantum mechanics. It's the framework that allows us to apply quantum principles or quantize all the matter and force fields of the universe except one, gravity. That's because in all quantum field theories, the matter and force fields are described as lying on top of a smooth, fixed, continuous grid of space-time, the special relativity stage.
So we see a big problem. Einstein banished the possibility of Heisenberg working with stochastic electrodynamic theory and left him with Minkowski's mathematical space-time. And the two just don't gel. Something deeper is happening here. We might be tempted to ask, what if space-time isn't the base layer of reality? What if there's a more fundamental description of physics which produces something that looks like space-time? In the 1970s, Jacob Bekenstein and Stephen Hawking stumbled on a compelling clue about the nature of quantum gravity. While using the equations of general relativity to explore black holes, Bekenstein and Hawking discovered that black holes act as if they have an entropy, and that quantum mechanics causes them to radiate particles in a particular way that gives them a temperature. But black holes, like everything else, need to comply with the laws of thermodynamics. So if black holes have an entropy, they must be made of more primitive parts, quantum microstates that can be thought of as the atoms of space-time. But Bekenstein and Hawking showed that with black holes, something surprising happens. A black hole's entropy is proportional to its area, more specifically the area of its event horizon or boundary. It's as if we can know all of the possible microstates of a black hole's interior structure just by counting the ways of arranging things on its surface. But how could a surface know everything about an interior volume? This strange finding is the best clue we have about the quantum nature of space-time. Things get more and more questionable. Roger Penrose told us that black holes are a robust prediction of general relativity. General relativity is a very dubious piece of mathematical fiction dependent on a mythomagical marriage between space and imaginary time. Robitaille has demonstrated that the only claimed picture of a black hole is a forgery, and black holes are an impossibility based on a false appraisal of the composition of stars. So I suspect that Professor Balasubramanian's speculations are being built on an ever-weakening foundation.
If a 3D object like a black hole is best understood using only two dimensions, could the same be true for the entire universe? In the 1990s, these questions coalesced into a compelling idea called the Holographic Principle. The Holographic Principle says that space-time is like a hologram, projected from the information available on some lower dimensional surface, like the boundary of the universe. On the holographic stage, the fabric of our reality, space-time, and gravity actually emerges from a quantum description in a lower dimension. If the holographic principle is true, the math describing gravity and the geometry of space-time should be equivalent to the math of quantum physics in a space-time of one fewer dimension. In the last few decades, physicists have searched for these mathematical equivalences with the goal of creating a dictionary of physics that bridges the dual descriptions. The best example so far is something called the ADS-CFT duality. This is a well-understood quantum theory known as a conformal field theory, or CFT. It has no gravity in it. Let's consider CFT in two spatial dimensions and, of course, time. This is a kind of space-time permitted in general relativity known as anti-de Sitter space, or ADS. It has gravity. Let's consider an ADS space with three spatial dimensions and time. The ADS-CFT duality is a dictionary that relates the math of the two theories. You can use it to calculate anything in one theory in the language of the other. We might describe this situation by saying that the ADS spacetime is emergent from the CFT because some of its dimensions appear out of the dynamics of the lower dimensional CFT. But if spacetime is emergent, what are the quantum processes that produce it? The holographic principle is one place where we've made lots of progress towards a quantum theory of gravity. There's a catch though. The ADS universe has a different space-time geometry than our own. So while the ADS-CFT duality is remarkable in its own right, it's not proof that we live on a holographic stage. Instead, you can think of it as a toy model for how space-time and geometry can emerge from entanglement. To make further progress, we have to find a way to extend these ideas to a model describing our universe with its particular geometry, particles, and peculiarities like dark energy. Ideally, we should also find a way to test the holographic principle experimentally. That's going to take lots of creative new ideas.
So, if they ever manage to get their holographic principle to make a mathematical model which might represent the universe we actually live in, a model which would emerge from their mathematical representation of another universe with one less dimension, they will then have to try to think up an experimental procedure to justify it. I wonder if they have ever heard of the scientific method. The method put forward by Francis Bacon, which begins with observation and measurements. The method which, when there are enough observations and measurements, to recognise patterns in those observations and measurements, proposes hypotheses to explain those patterns in the observations and measurements. The method which then goes on to experiments to test those hypotheses. The method of which Mendeleev said, science begins with measurement. It sounds to me as if what they are doing has nothing at all to do with science. As Sabine Hossenfelder has told us several times, it's just mathematical fiction, and science doesn't work like that. The Lord knoweth the thoughts of man, that they are vanity. He that sitteth in the heavens shall laugh. The Lord shall have them in derision. Thank you for joining me for this episode. If you enjoyed it, please like, subscribe and press the bell so that you'll be notified as I release new movies. If you'd like to support this project, you're welcome to do so through Patreon. Find a link on my channel banner and in the description below.